When engineers sit down to build a nuclear power plant, they actually spend billions of dollars explicitly designing it to fail, which, if you think about it for a second, is wild.
Right, it really is. It's a completely counterintuitive way to look at engineering, isn't it?
Exactly. I mean, we
Mhm.
usually think of safety as just making sure nothing ever breaks.
Yeah, but in the realm of extreme risk, assuming your systems will never break is, well, it's actually the most dangerous thing you can do.
And that is exactly what we are unpacking today. Welcome to the deep dive. We are keeping this under 17 minutes today just to really respect your time because we have our hands on a really fascinating stack of mechanical engineering blueprints.
Specifically, these are the lecture notes from a masterclass. It's ME 522 on nuclear reactor safety, taught at Fahd University of Petroleum and Minerals.
Yeah, and the mission here is to just kind of strip away the fear and the jargon that usually surrounds nuclear power. We want to look at the brilliant, almost philosophical risk management keeping these massive systems locked down.
Which is surprisingly applicable. I mean, the logic they use to prevent a nuclear meltdown is highly relevant to how you can bulletproof your own life or business.
Right. But to understand how they do it, we first have to understand what a nuclear plant is, like actually trying to achieve on a moment-to-moment basis.
Yeah. Before anyone designs a single valve or pump, the International Atomic Energy Agency mandates 3 non-negotiable safety functions.
The holy trinity of nuclear safety.
Exactly. Everything in the plant serves these 3 goals. You have to control reactivity, remove heat, and confine the radioactive material.
Okay, let's make this tangible. If we imagine the nuclear reactor as a wildly powerful, incredibly dangerous car, that first function controlling reactivity is basically your throttle and your brakes.
Right. Inside the core, uranium atoms are splitting, releasing energy and neutrons, which then smash into other atoms, creating a chain reaction.
And to control how fast that engine runs, engineers use physical control rods.
Yeah. And the mechanics of that are fascinating. The rods are made of materials like silver, indium, or cadmium, basically elements that absorb neutrons without splitting themselves.
So if the reaction's getting too hot, you just physically drop these rods into the core to soak up the neutrons and pump the brakes.
You do. Or you can dissolve a chemical called boron directly into the cooling water, which acts like a subtle, pervasive brake pedal you can slowly press or release.
Okay, so you can control the speed of the engine. But that brings us to the second function, the removal of heat. And this is where my car analogy requires a massive upgrade.
It really does.
Because in a normal car, if the engine is overheating, you just pull over, turn the key, and the engine stops generating heat. The radiator can basically clock out for the day. But in a nuclear plant, you can't just turn the reactor completely off.
No, you can't. And that is the defining challenge of nuclear safety. It's a phenomenon called decay heat.
Decay heat. Okay, walk me through that.
Well, let's say you hit the ultimate emergency brake, a reactor trip, or what they call a scram. All the control rods instantly drop into the core.
So the primary fission chain reaction stops immediately. Power output plummets.
Right. But the nuclear fuel is now packed with radioactive fission products that built up during operation. And these isotopes are inherently unstable.
So even though the main chain reaction is halted, these unstable atoms are still naturally decaying inside the fuel rods.
Precisely. And as they decay into stable forms, they throw off a massive amount of kinetic energy, which turns into heat. So the engine is technically off, but the engine block is still glowing white hot.
Oh, wow.
Yeah, this decay heat is actually the principal safety concern in light water reactors.
Which means your radiator has to keep running at full blast for days or even weeks after you turn the key off.
Yes. You have to maintain a constant, massive flow of cooling water, because if you lose that cooling capacity, the decay heat will simply melt the fuel cladding.
The metal tubes holding the uranium. And if those tubes melt, we hit a wall with the third fundamental safety function, confinement. If reactivity is the throttle and heat removal is the radiator, confinement is the seatbelt and airbags. It's the reinforced steel chassis keeping the public safe.
It's essentially a multi-barrier approach, designed like a Russian nesting doll. You have the fuel cladding as the first trap, then the heavy-duty primary cooling system pipes, and finally you wrap the entire thing in a concrete and steel containment building that is several feet thick.
Okay, so you have these 3 absolute goals: control the reaction, keep it cool, keep it contained. But here is where I get stuck. That's the ideal scenario. But the real world has, earthquakes, power grid collapses, and human error.
Yeah.
How do you guarantee the nesting doll stays intact when real life throws a curveball?
By fundamentally changing how you view failure. In nuclear engineering, they use a framework called defense in depth. The philosophy is simple but rigorous. You never rely on a single system, no matter how strong it is.
You build multiple, redundant layers of defense.
Right. If the first layer fails, the second layer is waiting.
And the framework breaks this down into distinct levels. Level 1 is all about prevention, right? Over-engineering the plant.
Yes. Ultra-conservative design margins, intense quality control, rigorous testing to ensure abnormal operations just don't happen.
But again, relying on perfection is a trap.
Exactly. So level 2 is control. Implementing automated systems to detect and intercept failures the moment they begin, long before an operator even notices a problem.
Wait, let me push back on this for a second. If you're adding thousands of backup sensors and automated valves, aren't you just creating a more complex machine? I mean, doesn't complexity inherently introduce more things that can break?
That is a brilliant point, and it's the exact paradox nuclear engineers wrestle with. Yes, complexity adds risk, which is why level 2 systems are designed to be entirely independent from the normal operating systems.
Independent how?
Well, take a coolant pump, for example. In level 2, you have acoustic sensors constantly monitoring the physical vibration of that pump. If the vibration hits a frequency, indicating a bearing might fail in a few hours, it doesn't just ring an alarm.
Right.
It automatically communicates with the control system to throttle back the load or switch to a backup without a human ever touching a dial. It intercepts the failure.
Okay, that makes sense. The system is actively trying to stabilize itself. But what if the bearing just shatters instantly? What if the pipe actually breaks?
Then you cross into level 3 mitigation. The goal here is to control accidents within what engineers call the design basis.
This is the concept that really shifted my perspective. Let's walk through the timeline of plant states. You start in normal operation, a minor glitch happens, and you move into anticipated operational occurrences.
Right.
But if a pipe actually ruptures, you enter the realm of design basis accidents. And when I first read that, I had to stop and reread it. Because if it is a design basis accident, that implies the accident is literally part of the blueprint.
It absolutely is. During the design phase, engineers use postulated initiating events, or PIEs. They sit in a room and explicitly define the disasters that could strike the plant.
Like a massive pipe severing completely, or a total loss of power.
Exactly. They calculate the physics of those exact disasters, and they build the safety systems specifically to absorb those hits.
There's an illustration often used in these courses to visualize this, and it perfectly captures the grim reality of risk management. It shows different versions of a plant operator. You start with the smiling normal operation guy. He looks great wearing glasses and a tie.
Yeah.
Next to him is the design basis accident guy. He looks stressed, his hair is blown back, and he has a Band-Aid on his face.
Right. He took a serious hit. The pipe broke. But he survived, and the radiation stayed contained because the plant was explicitly designed to handle that exact size of a pipe break.
But then the illustration keeps going. Next is the beyond design basis accident guy. His glasses are shattered. He's covered in heavy bandages. He is in severe accident territory.
And
finally, the way beyond design basis accident guy, who is essentially just a pile of smoking ashes with radiation symbols floating above it.
It's a dark joke, but the engineering truth behind it is profound. The entire goal of defense in depth is to build enough automated mitigation systems to stop the cascade of failure before you ever become the guy with the broken glasses.
Which brings up a massive logistical problem. It's one thing to brainstorm a worst-case scenario and build a backup cooling system. It's another thing entirely to mathematically guarantee that your backup system will actually stop the meltdown.
Yeah, you can't exactly build a multi-billion-dollar reactor, smash the main water pipe with explosives, and see if the backup pump turns on.
No, you definitely cannot do destructive testing on a nuclear core.
You have to prove the math before the fuel ever arrives on site. And the industry uses two deeply complementary methods to do this: deterministic safety analysis, or DSA, and probabilistic safety analysis, PSA.
Let's unpack the difference between those two, because they require completely different ways of thinking. Let's start with deterministic safety analysis. DSA is essentially the what-if method, right?
It is. It's highly rigid and conservative.
Yeah.
You assume the absolute worst-case scenario has definitively happened. For example, the largest coolant pipe in the plant has instantly snapped in half. You don't ask how likely it is to snap.
You just assume it did.
Right. Then you run the complex thermohydraulic physics equations to see if your backup safety systems can flood the core fast enough to keep the temperature below the melting point of the fuel cladding.
So it's binary. Does the core melt, yes or no? If the math says yes, you go back to the drawing board and make the emergency pumps bigger.
Exactly.
Yeah.
But DSA has a major limitation. Real life is rarely just one giant pipe breaking in isolation. Real life is a messy cascade of weird interconnected failures.
A valve sticks, which causes a pressure spike, which causes a minor leak, which shorts out an electrical panel.
Exactly. And that is where probabilistic safety analysis, the PSA, steps in. PSA doesn't just ask what if, it asks how likely. And to figure that out, engineers use a tool called fault tree analysis.
And this is purely deductive top-down logic. It's brilliant.
It is. Instead of looking at a single pump and asking what happens if this fails, you start at the very top with the absolute worst-case outcome, say a massive radiation leak, and you work your way down the tree.
You explicitly map out the multiple simultaneous failures that would be required to cause it. In safety analysis, the goal of building this massive tree is to find what are called minimal cut sets.
Yes, minimal cut sets.
Let me try to put this into an analogy because the concept is just so universally applicable. Think of a classic bank heist movie. The criminals want to rob the vault. To do that, they need to knock out the cameras, distract the guard, and blow the vault door. All three must happen.
Right.
In a normal movie, you watch them plan it step by step from the beginning. Fault tree analysis is a reverse heist.
Reverse heist. I like where this is going.
The engineers walk into a simulated, already empty vault, and they trace backward to figure out how it happened. They map out every possible pathway. Like, well, they could have cut the power, paid off the guard, and stolen the manager's key.
Or they could have dug a tunnel from next door, hacked the motion sensors, and used thermite on the hinges.
Exactly. Each of those combinations is a cut set. But why are they looking for the minimal cut sets?
Because the minimal cut set is the absolute easiest path of resistance. It's the minimum combination of security failures that allows the heist to succeed.
If you know the minimum combination, you know exactly where your system is most vulnerable. If the heist absolutely requires cutting the cameras and distracting the guard, the engineers don't need to build a thicker vault door. They just need to put a backup battery on the camera or put 2 guards on duty.
By breaking just one link in that minimal cut set, you prevent the entire disaster. That's an excellent translation of the concept. In a nuclear reactor, the heist usually begins with one of those postulated initiating events we mentioned earlier.
Like a LOCA.
Yes, a LOCA.
Yeah.
The loss of coolant accident. This is exactly what it sounds like, a breach in the primary pressure boundary. And the highly pressurized water cooling the reactor begins to escape. Engineers categorize them by size. Large LOCA, intermediate LOCA, or small OCA.
And they also analyze transients, right? Things that aren't physical breaks, but operational disturbances.
Yes, transients are a huge focus. Imagine an uncontrolled withdrawal of a control rod. Suddenly, reactivity spikes, heat spikes, and the system has to scramble to compensate. Or a total loss of feed water flow.
Which means your steam generators can no longer pull heat away from the primary system.
Right. In your reverse heist analogy, the LOCA, or the transient, is the moment the criminals step foot in the lobby. The fault tree analysis traces every single valve, backup generator, and safety injection pump to see if there's a minimal cut set that allows that initial spark to progress into a full core meltdown.
And the sheer volume of data processing required to map that out is staggering. You are looking at thousands of components, assigning a physical probability of failure to each one based on historical testing data, and then analyzing every possible way they could fail simultaneously.
It is mathematically exhausting. You end up mapping out sequences like small OCA occurs, reactor trips successfully, but safety injection train A fails, safety injection train B succeeds.
And you have to classify the end result of every single branch. Does it lead to a safely stabilized plant, or does it lead to core damage?
But the beauty of PSA is that it allows for incredible resource optimization. You don't just blindly throw money at making the concrete dome thicker if your fault tree reveals that the most highly probable minimal cut set is actually caused by a single faulty pressure relief valve.
You spend your budget fixing the valve.
Exactly. PSA is also the primary tool engineers use to identify what are known as cliff edge effects.
That phrase alone sounds terrifying. What is a cliff edge effect mechanically?
Mechanically, a cliff edge effect is a severe nonlinear failure. It's when a system relies on a specific threshold, and crossing that threshold by even a fraction of a percent causes a disproportionate catastrophic collapse.
Okay, give me an example of that.
Think about a backup battery system for the cooling pumps. If the power grid goes down, the batteries take over. For 59 minutes, the system looks perfectly healthy. The cooling is adequate, the dials are green, At 60 minutes, the battery voltage drops below the operating threshold.
And the pumps instantly shut off.
Right. The risk doesn't gradually increase. It goes from 0 to 100 in a millisecond. That is the cliff edge.
Yeah.
PSA helps engineers find those hidden thresholds so they can build immense safety buffers far away from the edge.
That makes so much sense. But as brilliant as this probabilistic math is, it is vital to acknowledge its blind spots. If you only look at the numbers, you might convince yourself a system is perfectly safe when it isn't.
Which is why relying solely on PSA is dangerous. The math struggles immensely with variables that cannot be easily quantified. I mean, how do you assign a failure probability to a software bug?
You can't. A physical steel pipe has a known wear and tear rate, but a piece of code controlling a valve.
Exactly. A hidden logic error might sit dormant for a decade and only trigger under a highly specific, totally unpredictable set of plant conditions.
The math also has a hard time with the human element, right? Common cause failures.
Precisely. If you have 3 redundant backup generators, the math assumes they operate independently. If one has a 1% chance of failing, the chance of all 3 failing at the same time is astronomically low.
But what if a single maintenance worker accidentally uses the wrong type of lubricating oil on all 3 generators during a routine check?
Now, the moment you need them, they all seize up simultaneously. The math rarely predicts the subtlety of human error. It certainly can't account for a poor overall safety culture where operators ignore warning lights because they're used to false alarms.
So, after diving deep into the holy trinity of safety, the layers of defense in depth, and the reverse heist logic of minimal cut sets, why does this matter to you, listening right now? Obviously, most of us are not designing light water reactors on the weekend.
It matters because the framework required to safely contain a nuclear reaction is arguably the ultimate blueprint for managing risk in any complex system in your life.
Exactly. This isn't just about uranium, it's about systems thinking. If you are launching a new startup, deploying a major software update, or even planning a massive life transition, you can apply this exact logic. Don't just plan for success, do a pre-mortem.
Start at the disaster.
Right. A total launch failure, complete bankruptcy, and build a fault tree. Work backward. What is the minimal cut set of events that would destroy this project?
Is it losing your lead developer AD, your primary investor, pulling out in the same week? If that is your minimal cut set, you now know exactly where to build your level 2 and level 3 defenses.
You shift your perspective from just hoping things go right to actively engineering resilience into your plan so they can absorb things going wrong. You move from the naive optimism of the smiling, normal operation guy to the calculated preparedness of someone who knows exactly what their design basis is.
Exactly.
Which leaves us with a provocative thought for today. Nuclear engineers spend billions building massive physical containment structures, and they run staggering mathematical models to hunt down their own blind spots. They're actively searching for hidden cliff edge effects in their systems.
Because they respect the complexity of what they have built.
Right. But we surround ourselves every day with incredibly complex, deeply interconnected digital and physical systems. Our automated finances, our cloud-based businesses, our smart homes. We rely on them completely, but we rarely map out the fault trees.
No, we don't.
So what cliff edge effects are hiding in the background of your life? What is the perfect minimal cut set of everyday failures? You know, a forgotten password, a momentary power blip, a delayed email just waiting to trigger a meltdown of your own.
It is definitely a question worth asking before the transient event actually happens.
It certainly is. Keep mapping out the fault trees around you, keep looking for those cut sets, and remember that sometimes the most resilient systems are the ones explicitly designed to handle failure. Thanks for joining us on this deep dive. We will catch you next time.